Hello everyone, welcome back to our channel, where today we're diving deep into the fascinating history of our planet Earth. Earth, our home, is a truly unique planet in the vast universe. It's been through many changes over its 4.5 billion year existence. From its formation to the creation of life as we know it today, the Earth formed over 4.6 billion years ago out of a mixture of dust and gas around the young sun. It grew larger thanks to countless collisions between dust particles, asteroids, and other growing planets, including one last giant impact that threw enough rock, gas, and dust into space to form the Moon. Although the rocks that record the earliest parts of Earth's history have been destroyed or deformed over time by more than 4 billion years of geology, scientists can use modern rocks, moon samples, and meteorites to figure out when and how the Earth and Moon formed, and what they might once have looked like. The Earth, like all the other planets in the solar system, started out its life as a disk of dust and gas orbiting the young sun. The dust particles were brought together by the forces of drag to form clumps of rock that grew into what scientists call planetesimals, which are tens to hundreds of miles across, and then to Mars-sized protoplanets by colliding with each other. Earth grew to its final major collision with another Mars-sized object. This last collision, also known as the moon-forming impact, was so large that in addition to adding lots of material to the Earth, there was enough energy to vaporize some of the rock and metal from both the proto-Earth and the impacting object. This vapor formed a disk around the Earth that eventually cooled and clumped together to become the Moon. We know this thanks to rigorous studies of meteorites and rock samples, including at the University of Chicago, in the 20th and 21st centuries. Understanding how the Earth and Moon formed is important for piecing together the history of the solar system and answering questions like how long planets take to form, what planets are made of, and what makes a planet suitable for life. This also guides planetary scientists in their search for other habitable worlds in our solar system and beyond. Scientists now think the Earth's story began around 4.6 billion years ago, and a disc-shaped cloud of dust and gas rotating around the early sun, made up of material left behind after the sun's formation. Within this disk, gas and dust particles of different sizes orbited the sun at slightly different speeds, allowing them to bump into each other and stick together. Eventually, they grew from tiny dust grains into boulders, then into larger planetesimals that range from miles to hundreds of miles in diameter. Because these planetesimals were larger than the boulders, they had strong enough gravity to pull neighboring planetesimals out of orbits and absorb them through collisions, enabling some planetesimals to grow bigger and bigger until they reach thousands of miles in diameter, about the size of the Moon and Mars. Some scientists believe that the oxygen isotopes are because the object that hit Earth was made up of the same mixture of meteorites as the Earth itself, potentially suggesting that the impactor planet formed close by in the solar system. Other scientists propose that after the impact all of the oxygen was able to move around in the hot vapor surrounding the Earth and Moon, mixing up all the different oxygen isotopes and erasing any original differences between the Earth and there. However, there are many differences between the chemistry of the Earth and the Moon, too. At the high temperatures reached during planetary impacts, many elements that we are not used to thinking of as gases, like potassium, zinc, and sodium, can exist as vapor. The concentrations of these volatile elements are much lower in lunar rocks than in rocks on Earth. One possibility is that the hot impact debris had a long time to evaporate these elements before it clumped together to form the Moon. Another is that when the Moon formed, it started off very hot with a deep magma ocean, like the Earth, and the low gravity and lack of atmosphere on the Moon allowed volatile elements that wouldn't escape from a larger object to evaporate into space. Both of these pieces of evidence are hard to explain without a giant impact. An impact origin for the Moon provides the high temperatures needed to explain the lack of potassium, zinc, and sodium on the Moon, and also an opportunity for lots of mixing between the proto-Earth and the material that would become the Moon. But when did this impact take place? After the Moon-forming impact, Earth was a very different planet from the world we see today, where the present-day Earth has oceans covering much of its surface. The early Earth was covered in a magma ocean, a layer of molten rock hundreds of miles deep that was melted by the energy released during the collision. Any water present would only exist as water vapor in the atmosphere. If that wasn't enough, the early sun was also far more active than it is today, blasting the entire solar system with UV radiation energetic enough to evaporate entire atmospheres. Over time, after the magma ocean cooled enough to form a solid surface, Earth's atmosphere was replenished by volcanic eruptions, as well as water and other gases delivered by comets and meteorites crashing into the surface. This was also the first step towards our planet developing plate tectonics. Plate tectonics describes the giant plates of crust that slowly move around Earth's surface over hundreds of millions of years. It not only produces new rocks at volcanoes where the plates are moving apart, but can also resurface an atmosphere back into the interior where plates are coming together. This process, known as subduction, carries rocks, water, and carbon dioxide trapped in minerals back into the Earth's interior, where they can drive future volcanic eruptions, continuing the plate tectonic cycle. Some planetary scientists believe that plate tectonics is essential for a planet to develop life. This is because the repeated production and destruction of crust by plate tectonics both releases carbon dioxide to the atmosphere and removes it, helping keep temperatures on Earth similar over billions of years. Whether a planet has plate tectonics is much more complicated than just having a solid surface, though, and might also depend on the types and amount of different asteroids, planetesimals, and protoplanets that the Earth is made of, because of the way different chemicals and minerals can change how planet interiors behave over billions of years. Although scientists agree that the Moon formed because of an impact, the details of the impact are still up for debate. Scientists still don't agree on how big the impacting object was, how fast it was traveling, what it was made from, or even whether we should be calling it there. Some scientists even argue that multiple impacts might have formed the Moon, instead of just one. Lab experiments help scientists better understand what happens to different rock types and elements under the extreme conditions of large impact events. Professor Nicholas Dowfer's research group at Chicago evaporates metals under a vacuum to simulate the conditions present in the cloud of impact debris, to try and explain why lunar rocks have so much less of elements like sodium, zinc, and potassium compared to the Earth. Some experiments can be too large for the lab, though, so computer simulations are also used to investigate the Moon-forming impact. These simulations enable scientists to virtually smash together the proto-Earth and different types of planetesimals at many speeds and angles to figure out what combinations of properties are able to form a Moon with the size and orbit we see today. In the future, new samples from the Moon could give planetary scientists a wider range of different lunar rock types to work with. This is important because new samples might record different pieces of the Moon's history that aren't present in the existing lunar rocks brought back by the Apollo missions. As measurement techniques improve, planetary scientists will also be able to measure unique signatures in lunar rocks and improve upon existing measurements. The more measurements scientists have, the more ways they can test different theories about how our Moon formed, its relationship to the Earth, and perhaps even how moons might be born around other planets far beyond our solar system. Thank you for joining us on this fascinating journey through time. If you enjoyed this video and want to learn more about our planet's history, don't forget to hit that like button and subscribe to our channel for more content like this. Until next time, stay curious about this amazing world we call home.